In this video, I will explain RC phase shift oscillator using Opamp. RC phase shift oscillator using operational amplifier using Opamp. Here Opamp is in inverting mode. That means feedback signal is applied to inverting terminal of that Opamp. That is minus sign. Non-inverting terminal of the Opamp is connected to ground. Here, three identical RC sections are used. Each section introduces 60 degrees phase shift. This one is 60. This one is 60. Total phase shift introduced by this feedback network is 60 plus 60 plus 60. That is equal to 180 degrees. Here the output of that inverting mode Opamp is applied to the feedback network. The output of the feedback network is applied to the inverting terminal of that Opamp, input to that Opamp. These two are 180 degrees phase shift is each other. Therefore, Opamp as an inverting amplifier introduces another 180 degrees because some phase shift is there, 180 degrees phase shift between this signal and this signal. Total phase shift introduced by this inverting mode operational amplifier is 180 degrees. Therefore, total phase shift is equal to introduced by the closed loop is equal to 180 degrees due to inverting mode Opamp, and another 180 degrees. Three identical RC sections are cascaded, introduces another 180 degrees. Total phase shift is equal to 360 degrees or 0 degrees around the loop. Output of the Opamp is given to the input of the feedback network. Output of the feedback network is given to the input of the operational amplifier. This one is Opamp inverting mode. This one is output. This one is input. Feedback network. FB. These are the given to like that. This one is this 180 degrees, 180 degrees. Total phase shift is 360 degrees. Coming to points. RC phase shift oscillator using Opamp is in inverting amplifier mode. RC phase shift oscillator using Opamp is in inverting amplifier mode. Thus, it introduces the phase shift of 180 degrees between the input and output. This one signal is this one, Opamp inverting mode, 180 degrees. The feedback network consists of three RC sections. Each RC section introduces 60 degrees phase shift. Already explained here. Each RC section introduces 60 and 60 degrees phase shift. Such a RC phase shift oscillator using Opamp is shown in the above figure. The output of the amplifier is given to the feedback network. The output of the amplifier is given to the feedback network. The output of the feedback network drives the amplifier. See, the output of that feedback network drives the amplifier. The total phase shift around a loop is 180 degrees of amplifier and 180 degrees due to three RC sections. Thus 360 degrees. This satisfies the required condition for positive feedback and the circuit works as oscillator. Mod A beta is greater than or equal to 1. Total phase shift introduced around the closed loop is 360 degrees. Advantages. The circuit is simple to design. Three identical RC sections are used under one op-amp, one feedback resistor, and R1, RF, op-amp, and three identical RC sections, and two power supplies. Can produce output over audio frequency range. Audio frequency range means 30 Hz to 30 kilohertz. Produces a sine wave within the range. Frequency range is from 30 Hz to 30 kilohertz. 20 Hz to 20 kilohertz. Audio frequency range is from 20 Hz to 20 kilohertz. Produces a sinusoidal output waveform. It is a fixed frequency. Once R and C values are selected, therefore frequency of oscillations is fixed one. F is equal, later I will derive. F is equal to 1 by 2 pi RC, 1 by 2 pi RC into root 6. R and C are fixed values, therefore it is a fixed frequency oscillator. Disadvantages. To vary the frequency, suppose vary the frequency F is varied based on the R and C elements. Values of R and C of all the three sections are to be varied simultaneously. If you want to vary the frequency F, R and C values of the identical RC sections are varied simultaneously, which is practically difficult. Hence, frequency cannot be varied. Frequency stability is poor due to change in values of various components due to effect of temperature raising, etc. Poor stability. Frequency value changes due to these due to changes in values of various components due to effect of temperature and aging, etc. Next, frequency of oscillations derivation. Frequency of oscillations derivation. Frequency of oscillations derivation. See this figure. This is the output of the V0 is the output of the op-amp is in inverting mode. This one is VF, output of the feedback. Consider this feedback network and have to determine the frequency of oscillations. Frequency of oscillations. C R C R. This one is V0. V0 means output of the op-amp is in inverting mode. VF is the output of the feedback network. That V0 is applied to this feedback network. Three identical RC sections. Apply mesh analysis. This one is these are the three capacitance. Capacitor reactance is equal to generally capacitor reactance is equal to capacitor reactance is equal to 1 by j omega c. X is equal to 1 by j omega c. Numerator and denominator is multiplied with j into j square minus j by omega c, that is equal to minus j by minus j into x minus j x. Since x is equal to 1 by omega c. X is equal to 1 by omega c. Therefore, redraw the circuit diagram. Minus jx or minus jx R minus Jx R. This one is Vf. Feedback voltage is Vf. This one is V naught. Output of the Opamp is in inverting mode is applied to input to the feedback network. SI to 3 loop currents I1, I2 and I3. Apply mesh analysis above equation, above network, the above network. Consider first loop V naught is equal to R and minus Jx. These are the two elements are present in the first loop. Therefore, sum of these two elements into that loop current. R minus Jx into that loop current is I1. This R is common to first loop as well as second loop. That is the reason minus R into I2. There is no I3 current is not involved here. I3 current is not involved. And apply mesh analysis to second loop 0. This R is common to second loop and the first loop. That is the reason minus R into I1. This is equation number 1. Plus second loop current I2 into sum of these three elements impedances values R, R plus R minus Jx. This is the R is the resistance common to second loop and third loop minus I2 into R. This is the second equation. Coming to third equation, 0 is equal to this R is common to second loop and third loop minus I2 into R. There is no way to connect this first loop plus I3 into R plus R 2R minus Jx. R plus R minus Jx. See the third equation. And the fourth equation is Vf is equal to, this is the Vf. Vf is equal to I3 into R. I3 into R. This is the feedback network. This is the feedback network. Input to that feedback network is V naught. Output of that feedback network is Vf. Beta is equal to Vf by V naught. Beta is equal to Vf by V naught. First of all, we have to find out the Vf value and then substitute in that equation. Mod A beta greater than or equal to 1. That means mod A mod beta greater than or equal to 1. First of all, we have to calculate I3 current by using these three equations, by using Carson's rule. After that, Vf is calculated. Beta is equal to Vf by V naught. And beta is substituted here. We will get mod A value. Okay. These three equations are converted into matrix form. This is the matrix form. R minus Jx. First equation R minus Jx minus R 0 minus R 2R minus Jx minus R 0 minus R 2R minus Jx I1 I2 I3 I1 I2 I3 and V naught 0 0, V naught 0 0. These three equations are converted into matrix form like that. I have to calculate I3 according to Carson's rules. I3 is equal to delta 3 by delta. I3 is equal to delta 3 by delta. Delta, we have to calculate delta value. Delta is equal to mod of R minus Jx minus R 0 minus R 2 R minus Jx minus R 0 minus R 2R minus Jx. First calculate delta value. Here from the first row, R is common term. Second row is also R. Third row is also R. 1 minus J into X by R. R is common term. Minus 1, 0, minus 1. 2 minus J into X by R. Minus 1, 0, minus 1. 2 minus J X by R. This is the delta value calculation. R cube. Let X by R is equal to alpha. We know that X is equal to 1 by omega C. X is equal to 1 by omega C. Therefore, 1 minus J alpha minus 1, 0, minus 1, 2 minus J alpha minus 1, 0, minus 1, 2 minus J alpha. Calculate this value, calculate this delta value. R cube 1 minus J alpha into 2 minus J alpha whole square minus into minus plus and minus 1 plus 1 into minus 1 into 2 minus J alpha minus 2. This is the 1 minus J alpha and 2 minus J alpha into 2 minus J alpha, 2 minus J alpha whole square minus into minus plus 1 minus of 1 minus 1 plus 1 into minus of minus 1 plus 1 into minus 1 into 2 minus J alpha. Therefore, plus 1 into J alpha minus 2. Here minus 1 into 2 minus J alpha is J alpha minus 2. Simplify this expression. That is equal to R cube 1 minus J alpha A square 4 minus alpha square plus B square means J alpha square. J square is minus 1 minus alpha square minus 4AB minus 2AB. 2 into 2, 4. 4 J alpha minus 1 plus J alpha minus 2 plus J alpha minus 2. R cube 1 minus J alpha 4 minus 1, that is 3 3 minus alpha square minus 4j alpha plus j alpha minus 2. Simplify this one. That is equal to r cube. 1 into entire term, that is 3 minus alpha square minus 4j alpha. Minus j alpha is multiplied with all these terms. Minus into plus minus 3j alpha minus into minus plus j alpha cube minus into minus plus j into j square again minus 4 alpha into alpha 4 alpha cube plus j alpha minus 2 j alpha minus 2. 1 into 3 minus alpha square minus 4j alpha minus 3j alpha minus into minus plus j alpha cube minus into minus plus minus into minus plus this one is alpha square minus into minus plus j into j square j into j square, that is minus 4 alpha square alpha into alpha square 4 alpha square plus j alpha minus 2 r cube 3 minus 2, that is 1 minus 4 alpha square minus alpha square, that is minus 5 alpha square plus j alpha cube. Here minus 4j alpha minus 3j alpha minus 7j alpha. These two are minus 7j alpha plus j alpha minus 6j alpha minus 6j alpha. Therefore r cube into 1 minus 5 alpha square. J term is constant, j into alpha cube minus 6 alpha. This is the delta value. Next, calculate delta 3 by using three equations. Delta 3 is equal to r minus jx minus r. By using these three equations, V naught is equal to r minus jx into I1 minus r into I2. 0 is equal to minus r I1 plus I2 into 2r minus jx minus I2r. 0 is equal to minus I2r plus I3 into 2r minus jx. By using these three equations, I have to calculate delta 3 value. Delta 3 value. Delta 3 is equal to last third column is replaced with V0, 0, 0, and the first two columns are equal. That means r minus jx minus r minus jx minus r minus jx minus r. The remaining second minus r 2r minus jx minus r 2r minus jx 0 into 0 third one 0 minus r 0 minus r. Therefore, delta 3 is equal to r minus jx into this one into this one and this one 0 r minus jx into 0 here plus r into minus r into 0 minus of minus 0, that means r into 0 plus v naught into here v naught minus r into minus r square. Delta 3 is equal to v naught r square. Delta is equal to, we know that delta is equal to r cube into 1 minus 5 alpha square 1 minus 5 alpha square plus j into alpha cube minus 6 alpha cube minus 6 alpha. We know that Vf is equal to output beta is equal to output voltage by output of the feedback voltage by input to the feedback network. Beta is output voltage of feedback network to input voltage of feedback network. Output voltage is Vf, input voltage is V naught. Vf is equal to I3 into R by V naught. We know that I3 into R is equal to delta 3 by delta. Delta 3 by delta R by V naught. Delta 3 is equal to V naught square into V naught into R square. V naught into R square into R by delta value is R3 into 1 minus 5 alpha square plus j into alpha cube minus 6 alpha into V naught. This V naught is cancelled. R cube and R cube is cancelled. Finally, beta feedback network beta is equal to 1 by 1 minus 5 alpha square plus j into alpha cube minus 6 alpha. We know that total phase shift loop gain value mod A mod beta greater than or equal to unity. Therefore, mod A and mod beta value is here 1 by 1 minus 5 alpha square plus j into alpha cube minus 6 alpha mod A beta is equal to total phase shift degrees are the minus degrees. 0 degrees are 360 degrees. Tan inverse of 0 by something, that is 0. 0 by something is some b a plus jb. Tan inverse of b by a. J quotient b is equal to 0. Therefore, tan inverse value is equal to 0 degrees. Therefore, J quotient value is equal to 0 because the loop gain is either 0 degrees or 360 degrees. J quotient is 0. that means alpha cube minus 6 alpha is equal to 0. Alpha cube is equal to 6 alpha. Therefore, alpha square is equal to 6. Alpha is equal to root 6. We know that already defined alpha is equal to x by r root 6, but x is equal to initially defined 1 by omega c r into is equal to root 6. Omega is equal to 2 pi f cr is equal to root 6. Therefore, f is equal to 1 by 2 pi rc root. This is the frequency of oscillations of the Opamp RC phase shift oscillator. But mod A, mod A, mod A, mod beta is equal to mod A into 1 by 1 minus 5 alpha square. Alpha square, alpha is equal to root 6, alpha square is equal to 6. That is equal to mod A 1 minus 1 by 1 minus 5 into alpha square is equal to 6. That is mod A by 1 by 1 minus 50. Mod A by 1 by 29. Loop gain mod A mod beta is greater than or equal to 1. Therefore, mod A by mod A into mod beta is 1 by 29 greater than or equal to 1. Therefore, mod A greater than or equal to 29. Gain of the amplifier is greater than or equal to 29. The op-amp is in inverting mode. Therefore, gain of the op-amp in inverting mode is generally U is equal to minus RF by R1. Inverting mode minus sign indicates 180 degrees phase shift between input and output. Mod A means RF by R1. Here mod A is equal to 29. Therefore, RF is equal to 29 times R1. This is the total analysis is complete.